The universe's planet? Question: are we the weird ones? Is Earth a normal planet? Or are we the strange ones, living on a rare kind of world, in a universe filled with far weirder possibilities? Most of us grew up with a very simple picture of planets. There were the small rocky ones near the star, the giant gas worlds further out, and the icy leftovers in the dark. Rocky, gas, icy, neat, tidy, easy to remember. But while that picture worked for our textbooks, it collapsed almost instantly the moment we started finding planets around other stars. Because the exoplanet data has shown us something extraordinary. The universe does not respect our categories. We have found molten lava worlds, with dayside temperatures hot enough to vaporize rock. We have discovered bloated cotton candy giants, so puffy that their density is lower than foam. We have seen planets that may be rich in carbon, where deep underground, entire mantles could be made of diamond. And drifting between the stars, there are rogue planets, torn from their systems, wandering through eternal night with no star at all. So it's time to find out the truth. Is Earth a typical outcome of planet formation? Or is our blue, life-bearing world an outlier in a cosmic zoo of extremes? This matters far beyond curiosity. In the hunt for alien life, knowing all the different types of planets the universe can build tells us where to look, which atmospheres to study, and which headlines might actually hint at a second Earth-like world. It should be noted that when astronomers talk about planet types, we are not just being poetic. We are trying to sort thousands of worlds into families that share the same basic physics. Tiny airless rocks hugging their star, super-Earths and mini-Neptunes wrapped in thick atmospheres, hot Jupiters skimming the stellar surface, cold ice giants, steam worlds, super-puffs, carbon planets, and more. Each type forms in a different part of its system, under different conditions, and each offers a different chance for a habitable environment. This means there is a deeper mystery hiding underneath all the exotic names. If we lined up every major kind of planet the universe can make, from scorched pebbles barely larger than our moon, to mega-Earths with crushing gravity, to swollen super-puffs that are almost more atmosphere than planet, where would Earth actually land on that spectrum? Are we sitting in the crowded middle, or perched on the edge of something rare? By the end of this video, you will be able to look at any exoplanet headline and immediately know what kind of world it is, how it probably formed, and what that means for life. So, let's begin our tour of every type of planet in the universe, why planet types matter, from cosmic gravel to cradles of life. So if we can sort every world in the universe into types, why does that actually matter? These are not just pretty dots on a star chart. Planets are where the action happens. A star sets the stage with light and heat, but the planet is the theater where atmospheres, oceans, and potentially life appear. This means the type of planet decides almost everything that follows. Is the surface molten rock or solid ground? Is there an atmosphere thick enough to trap heat, but thin enough to let light through? Is there any chance for liquid water to sit there for billions of years without boiling away or freezing solid? In the hunt for alien life, those questions are not abstract. They are the difference between a world like Venus, wrapped in a runaway greenhouse, and Earth, balanced in its Goldilocks zone with oceans and a breathable atmosphere. Two planets, similar size, similar orbit around their star, completely different outcomes. It should be noted that from far away, both of them would just look like small, pale points of light. Different planet classes naturally live in different temperature ranges and chemical regimes. A hot Jupiter grazing its star in a 2-day orbit will have an atmosphere stripped and blasted by radiation. A mini-Neptune far out in a cold system might hide a deep ocean under hydrogen clouds. Super-Earths can hold on to thick atmospheres. Tiny sub-Earths may lose theirs entirely. Each category shifts the odds for stable climates, for liquid water, for anything we would dare to call habitable. But while we talk about these worlds in such detail, we almost never see them directly. Most of the time, all we have is a faint dip in starlight as a planet passes in front, or a tiny wobble in the star's motion as gravity pulls back and forth. From that minimal data, plus some physics, we infer radius, mass, density, and then we try to guess the type. Rock or gas, ocean or ice, thin atmosphere or super puff. So it's time to find out the truth about how far those inferences can really go. astronomers have now cataloged thousands of these strange worlds, and the result looks less like a tidy list and more like a cosmic planet zoo. We see hot Jupiters roasting near their stars, super puffs lighter than cotton candy, compact mega-Earths, and whole families of super-Earths and mini-Neptunes that our own solar system somehow skipped. The challenge is to turn this chaos into a classification system that does more than label. It must actually predict properties and habitability. Optimistically speaking, if we can connect formation, type, and climate, we will know which planets deserve our closest attention. So, let's begin at the very start. How do you build such different worlds from the same swirling disk of dust and gas? And why does that first step already choose which ones might one day host life? From dust to worlds. How planet types are forged. To understand every type of planet, we first have to ask a deceptively simple question. What does a newborn solar system actually look like? Not a neat row of worlds, but chaos. When a star ignites, it does not appear alone. It is wrapped in a vast, swirling cocoon of gas and dust. Gravity pulls this material inward, but because it is rotating, it flattens into a thin, spinning disk around the young star. This is the protoplanetary disk, and for a few million years, it is the workshop where every future planet in the system is assembled. Inside that disk, the raw ingredients are surprisingly small. Microscopic dust grains collide at low speeds and stick together through static electricity and molecular forces. They grow into fluffy clumps, then pebbles, then boulders. Over time, these fragments become kilometer-scale planetesimals, big enough that gravity takes over and pulls more material in. It should be noted that this is where chance and violence start to rule. As planetesimals collide and merge, they build planetary embryos, roughly Moon to Mars size. Some survive, some are shattered, and some are thrown into new orbits. But while this process sounds random, there is an underlying pattern written into the temperature of the disk itself. Closer to the star, the disk is hot. Here, only the most robust solids survive, metals like iron and nickel and rocky silicates. This means the building blocks are dense and compact, so we naturally get small rocky worlds, with iron cores and thin atmospheres at best. Move outward and the temperature drops. At a certain distance, water, carbon dioxide, methane, and other ices can finally freeze instead of evaporating. This invisible boundary is called the snow line. Beyond the snow line, something dramatic happens. Suddenly, all those frozen volatiles join the solid inventory, massively increasing the amount of material that can be packed into a growing core. Cores there can bulk up to several Earth masses much faster. In the hunt for alien life, this is crucial because if a core grows quickly enough, while the gas disk still exists, it can capture a huge hydrogen and helium envelope and become a gas giant. So, inside the snow line, we expect chains of rocky, potentially Earth-like planets. Outside, we expect icy cores wrapped in thick atmospheres, our Jupiters and Neptunes. So, let's begin to connect the dots. Location in the disk quietly chooses which types of planets are even possible. Pattern interrupt. What if that neat picture is wrong? Because the disk itself is not static. Giant planets can migrate inward, dragging smaller bodies with them. Gravitational encounters can scatter worlds into eccentric orbits, or even eject them into interstellar space. So it's time to find out the truth. The universe starts with an orderly blueprint, then scrambles it, creating hot Jupiters skimming their stars, mini-Neptunes in the Goldilocks zone, and entire planetary families that seem to break every rule we have just laid down. Rocky Worlds 101, the classic terrestrial planet template. If the universe scrambles the rules, what is the rulebook it starts from? Before we dive into lava planets, ocean worlds, and all the exotic categories, we need the basic template, the classic rocky planet. These are the terrestrial planets. In simple terms, they are worlds made primarily of rock and metal, with thin atmospheres or none at all. In our own system, Mercury, Venus, Earth, and Mars are the local prototypes. They all orbit the same star. They all formed from the same disk of material, and yet their surfaces and climates could hardly be more different. So, let's begin by asking, what do they actually share underneath all that variety? Deep down, a terrestrial planet is layered. At the center, an iron-rich core. Around it, a thick rocky mantle. On top, a relatively thin crust. This means gravity increases with mass and density, and that gravity controls almost everything that follows. Stronger surface gravity helps a planet hold on to an atmosphere. A hot, convecting mantle can drive plate tectonics, recycling crust, and regulating climate over billions of years. It should be noted that Earth is the only planet we know with active plate tectonics today, but Mars shows ancient tectonic scars, and even little Mercury has a large metallic core that shaped its past. Size is critical. Below Mars's mass, a sub-Earth world cools fast, loses internal heat, and struggles to keep a substantial atmosphere. Above Earth's mass, you enter the realm of super-Earths, rocky planets up to a few times our mass, with crushing surface gravity and deep mantles that may stay molten for eons. Push the mass too high though, and the story changes. The planet's gravity becomes strong enough to capture and keep a thick envelope of hydrogen and helium from the protoplanetary disk. This means the world stops being a bare rock and starts to blur into a mini-Neptune. So why do Mercury, Venus, Earth, and Mars look so different if they share the same basic architecture? Because atmosphere thickness, distance from the star, and greenhouse gases can transform that simple rocky template into almost anything. Move a world slightly closer in, wrap it in carbon dioxide, and you get Venus, a 460-degree hellscape with crushing pressure. Place a similar planet a bit farther out, with liquid water and a balanced greenhouse effect, and you get Earth's temperate oceans and a surface that can be truly habitable. In the hunt for alien life, we often imagine Earth like twins. But while that is an appealing picture, most rocky planets we are finding are not tidy Earth clones. Many hug their stars so tightly that they are tidally locked, with one hemisphere in endless day and the other in perpetual night. Some are airless, more like scaled-up Mercuries. Others may be wrapped in global magma oceans or buried beneath planet-wide seas. Optimistically speaking, this is just the beginning of the rocky family tree. Next, we will see how far the universe pushes this template into the extreme: super-Earths and sub-Earths, the missing sizes in our backyard. So if rocky planets can be scaled up and melted down, how small and how large can they really get before they turn into something else entirely? In the hunt for alien life, this missing middle of planet sizes might be the most important part of the whole story. So let's begin on the small side. Below Earth, we find what astronomers call sub-Earths, rocky planets, and large moon analogs, with diameters smaller than our world and gravity that can barely hang on to an atmosphere. Many of them are probably more like oversized versions of Mercury or our own moon, airless or wrapped in only the thinnest veil of gas. This means their skies could be black even at noon, their surfaces blasted directly by their star. But while these worlds might be everywhere, they are also experts at hiding. Sub-Earths produce only the faintest dips in starlight when they orbit across their star, and their gravitational tugs are almost lost in the noise of our data. It should be noted that most of the small planets we do see are the easiest cases, close in, hot, and often stripped. Farther out, there could be Mars-sized or even smaller planets with pockets of ice, patchy atmospheres, and just enough warmth to flirt with being marginally habitable. Now, we dial the size knob the other way. Between about 1 and 2 times Earth's radius, and up to roughly 10 Earth masses, we enter super-Earth territory. These are still primarily rocky planets, but with higher gravity, thicker atmospheres, and probably more vigorous geology. Imagine standing on a planet where every step feels twice as heavy, where volcanoes are fed by a restless interior, and where a stronger magnetic field shields the surface from the star's radiation more effectively than Earth's does. Here is the strange part. When we look across the galaxy, super-Earths and their puffier cousins, mini-Neptunes, are the most common planet sizes we find, yet our own solar system jumps right over them. We go from sub-Earths like Mars and Mercury straight up to Neptune, with nothing in between. So it's time to find out the truth. Our local planet lineup is not typical at all. For habitability, that has huge consequences. A super-Earth in the Goldilocks zone could have a dense, stable atmosphere and deep global oceans that resist climate swings for billions of years. But that same gravity might limit mountain heights, change how plate tectonics works, and make human-style mobility extremely difficult. Would complex, Earth-like life thrive under such weight or evolve into something very different? And there is a sharper edge to this puzzle. At what point does a super-Earth stop being a scaled-up rock and start inflating into a gas-rich mini-Neptune, wrapped in hydrogen and helium? Optimistically speaking, there might be a narrow band where both rocky super-Earths and small mini-Neptunes can host life in very different ways. But to understand that boundary, we have to cross it and meet the strangest planets yet, lava worlds and magma oceans. When rock becomes atmosphere, To cross that boundary, we have to leave familiar rock behind and visit worlds where rock itself melts, boils, and even turns into atmosphere. What does a rocky planet mean when the rocks are literally in the sky? So, let's begin with the most extreme members of this family, ultra-short period lava worlds. These are planets like 55 Cancri E and K2 141b, orbiting so close to their star that a full year is shorter than an Earth day. 55 Cancri E circles its star in about 18 hours. K2 141b does it in just over 6. Imagine sunrise, noon, sunset, and New Year's Eve, all before you finish a work shift. At those distances, the star fills much of the sky, and the energy pouring in is relentless. Surface temperatures on the day side can exceed 2000 degrees Celsius, hot enough to keep entire hemispheres as global magma oceans. This means the ground is not solid rock, but a churning sea of molten silicates and metals, glowing orange-white, constantly stirred by tides and stellar heating. In the hunt for alien life, these are not habitable worlds, but they show us how far the rocky category can be pushed. Most of these lava planets are tidally locked. One hemisphere always faces the star, permanently frozen in a hellish noon, while the night side never sees the star at all. But while the day side is an ocean of lava, the night side can be hundreds or even more than 1,000 degrees cooler. That is still incredibly hot by Earth standards, yet cool enough that parts of the surface may solidify into a crust of black, glassy rock. Here is where things become truly alien. On the day side, the magma ocean is so hot that some of the rock literally vaporizes, turning into a mineral-rich atmosphere made of sodium, silicon monoxide, iron, and other elements we usually meet as solid stone. It should be noted that this is not an atmosphere like Earth's, with water clouds and nitrogen. It is more like the exhaust of a rock furnace, constantly evaporating from the surface. Now picture the rock rain cycle. Vaporized rock is blasted by intense stellar radiation and winds toward the night side, where the air cools. There, those minerals condense out of the atmosphere, forming clouds and then falling back to the surface as droplets of molten rock or shards of solid mineral snow. That material can flow or creep back toward the day side, be remelted in the magma ocean, and the whole cycle repeats. So it's time to find out the truth about classifications. We still call 55 Cancri E a rocky super-Earth, yet it looks nothing like Earth. Optimistically speaking, this means every broad class we use, rocky, icy, gaseous, actually hides a huge spectrum of extremes. And if rock can become atmosphere, what happens when we push gases and ices to their own breaking points? Ocean worlds and water planets, global seas without continents. If rock can become atmosphere, what happens when water refuses to behave like an ocean at all? Because out there, the universe builds planets that are not Earth with seas, but seas that just happen to have a planet buried underneath. So, let's begin with the definition. When astronomers talk about ocean worlds, they do not just mean a planet with big oceans like Earth. They mean a world where liquid water forms a global or near-global layer, possibly hundreds of kilometers deep, with no exposed continents anywhere. From orbit, there is no hint of land, just endless blue, or perhaps a dull, cloud-choked gray. How do you make a planet that wet? In the hunt for alien life, this question matters a lot. The leading idea is that these worlds form beyond the snowline, in a young planetary system, the region where water freezes into solid ice grains. Out there, it is easy to pile up enormous amounts of ice. Later, migration toward the star, or slow internal heating from radioactive elements, melts that ice into a deep global ocean. This means a planet that originally looked like a frozen comet on steroids can transform into a water-rich super-Earth. But while the surface might look deceptively simple, the interior is anything but. Under hundreds of kilometers of water, pressure climbs to millions of times Earth's sea level value. Water responds by changing phase into exotic high-pressure ices, solid forms that are denser than liquid and can exist at thousands of degrees. It should be noted that this ice is not like the stuff in your freezer. Instead, it can form a thick shell beneath the ocean, separating the liquid water from the rocky mantle below. That boundary is crucial. On Earth, direct contact between ocean and rock drives chemistry, plate tectonics, and long-term climate cycles. On a deep-water planet, the high-pressure ice layer could act as an insulating lid, locking the rock away. Classic Earth-style plate tectonics may be suppressed, nutrients from the interior might struggle to reach the surface ocean, and the familiar land-based feedbacks that stabilize climate, like the carbon silicate cycle, may never get started. So are these planets less habitable, or just habitable in a very different way? On the plus side, a global ocean can be remarkably stable over billions of years, and water is abundant everywhere you look. Optimistically speaking, that is an enormous volume, in which life could arise and adapt, perhaps around hydrothermal vents at the base of the ocean, or within the high-pressure ice itself. But here is the twist. If life does emerge in those deep, dark oceans, would we ever know? From interstellar distances, an ocean world might just look like a slightly puffed-up, water-rich mini-Neptune with a thick atmosphere. No continents, no obvious seasonal vegetation signals, maybe just subtle hints of water vapor and clouds. So it's time to find out the truth about our biases. We fixate on Earth-like mixed land-ocean planets, yet ocean worlds around red dwarf stars and sun-like stars alike could be far more common. If most of the universe's habitable real estate is hidden beneath global seas, then our next question is obvious. What happens when you strip almost all the gas away, leaving bare rock and ice behind? Gas giants, hot Jupiters, warm Saturns, and our weird solar system. So if stripping gas away gives us bare rock and ice, what happens when a planet keeps almost all of its gas instead? In the hunt for alien life, this is a crucial question, because the biggest planets in a system often decide the fate of the smallest. Gas giants are the heavyweights of the planetary universe. At their hearts, we think there is a dense core of rock, metal, and ice only a few times Earth's mass. Wrapped around that, though, is an enormous envelope of hydrogen and helium, sometimes hundreds of Earth's worth of gas. Jupiter and Saturn are our local examples, but it should be noted that once we started finding exoplanets, we discovered that gas giants come in many more flavors than our textbooks predicted. Take hot Jupiters. These are planets with roughly Jupiter's mass, yet they orbit so close to their star that a year can be shorter than an Earth day. Their atmospheres are blasted to thousands of degrees. Molecules are ripped apart, and winds can roar around the planet at kilometers per second. Some even show clouds of vaporized metals. But while they look extreme, they also gave us one of the first big clues that planetary systems can be radically different from our own. How do such giants end up hugging their stars? They almost certainly did not form there. Gas giants are thought to assemble beyond the snowline, the cool region of a young disk, where water and other ices can freeze and help build massive cores. This means hot Jupiters likely migrated inward, interacting with the gas disk or with other planets. In the process, they can scatter smaller worlds, strip away atmospheres, or even fling rocky planets out of the system entirely. So, let's begin to see them not just as curiosities, but as wrecking balls that can reshape an entire planetary architecture. Farther from their stars, we find warm and cold giants. Their atmospheres are cooler, allowing clouds of water, ammonia, and other compounds to condense, more like the banded, stormy faces of Jupiter and Saturn. They may host layered weather systems, deep lightning storms, and long-lived vortices. Optimistically speaking, large moons around these giants could even sit in a local Goldilocks zone, with conditions that might become habitable. And our solar system? So it's time to find out the truth about how strange it really is. We have cold giants, but no hot Jupiter. That absence may have spared the inner rocky planets from catastrophic migration and violent scattering. Our quiet configuration could be comparatively rare, and possibly essential for Earth-like worlds to survive long enough for life to emerge. If giant planets can both protect and destroy, what about the worlds that sit between categories, blurring the line between rocky and gaseous? Those are the planets that truly rewrite the rules. Ice giants and mini-Neptunes, the universe's favorite planet size. So what happens when a planet is too big to be a comfortable rocky world, but too small to be a classic gas giant? These in-between worlds are not rare exceptions. They are, as far as our data can tell, the universe's favorite size of planet. So, let's begin with the ice giants we know best, Uranus and Neptune. Unlike Jupiter and Saturn, which are mostly hydrogen and helium, these planets are dominated by so-called volatile ices, water, ammonia, and methane mixed into a hot, slushy mantle wrapped around a dense core. Above that sits a thick envelope of hydrogen and helium, topped with cold, windy atmospheres that hide interior pressures so high that water behaves more like a strange, electrically conducting fluid than any ocean on Earth. This means that even though we call them ice giants, they are not frozen snowballs. Deep inside, they are scorching, compressed worlds. And when we look out at other systems, we see countless versions and variations on this theme, many of them scaled down. Those are the mini-Neptunes. Mini-Neptunes typically span about 2 to 4 times Earth's radius. They are too large to be simple super-Earths, yet far smaller than Neptune. It should be noted that even a modest hydrogen and helium envelope on a rocky or icy core can puff a planet up dramatically, so from a distance they look like small ice giants. Instead of having a solid surface, they probably host deep atmospheres fading into layers of high-pressure water, exotic ice, or supercritical fluids that do not behave like familiar liquid or gas. When we survey thousands of exoplanets, one pattern keeps appearing. The most common worlds we see are not Earth-like planets or Jupiter-like giants, but super-Earths and mini-Neptunes packed close to their star, often well inside what we would call the Goldilocks zone. In the hunt for alien life, this is both exciting and frustrating. We have discovered the galaxy's default outcome, but it is not clear whether these intermediate planets can ever be truly habitable. So it's time to find out the truth about how they form. A small change in mass, or in the timing of when a growing core meets the gas of the protoplanetary disk, can decide its fate. Build up a bit too slowly, and you might end up as a dense super-Earth with only a thin atmosphere. Cross a critical threshold while gas still surrounds the young star, and the same core can capture a thick, puffy envelope and become a mini-Neptune instead. That raises a crucial question. Can mini-Neptunes ever shed enough atmosphere to uncover a rocky, potentially habitable surface? Or are they permanently cloaked, high-pressure hothouses hostile to life as we know it? Optimistically speaking, some may be stripped by their star into new kinds of worlds we have not yet seen. To test that idea, we have to look at the planets that push this transformation to the extreme. Super puffs and mega-Earths, cotton candy versus cosmic anvils. Some planets are light as a whisper, others are cosmic anvils. If mini-Neptunes are the middle ground, then super puffs and mega-Earths are the extremes that stretch our imagination of what a planet can be. So let's begin with the strangest lightweights in the universe. Super puff planets look enormous in our data, with radii close to Jupiter's, but when we weigh them using their star's wobble, we find masses only a few times that of Earth. This means their average density is lower than cotton candy. The Kepler-51 system is the poster child. Its planets are so puffed up that if you could scoop out a chunk the size of water on Earth, it would float away like a balloon. How does a planet become that absurdly fluffy? It should be noted that gravity is the sculptor here. With low surface gravity and intense heating from their nearby star, the upper atmosphere can swell to huge sizes. Hydrogen and helium get energized, expand, and form a vast, tenuous envelope. From far away, the planet looks huge. Up close, most of that size is almost empty space. In the hunt for alien life, these worlds are more like failed mini-Neptunes than habitable oases. Their atmospheres are so extended that they may be slowly escaping into space, creating long, invisible tails of gas. Optimistically speaking, over billions of years some of that gas might be stripped away, but right now they are bloated, delicate giants, not Earth-like refuges. Now, pattern interrupt. Take that mental picture of a fluffy cotton candy planet and flip it. Imagine a planet the same size in radius, but with so much rock and metal packed inside that it weighs 10, 15, even 20 times as much as Earth. This is the realm of mega-Earths. Mega-Earths are ultra-dense rocky planets that refuse to stop growing. They may form in metal-rich disks, where there is simply more solid material to build with, or through mergers of several large rocky worlds in a crowded system. But while superpuffs have low gravity and swollen atmospheres, mega-Earths crush gas down, leaving relatively thin atmospheres over an ironstone interior. From a distance, here is the problem. A mega-Earth and a small gas-rich planet can have very similar sizes. Transit data alone only tells us the radius. To know whether we are looking at a true rocky behemoth or a disguised mini-Neptune, we need precise mass and radius together, and sometimes atmospheric spectra from instruments like JWST. This means we cannot trust appearances in exoplanet headlines. Two Earth-sized planets might share a diameter but hide utterly different internal structures and very different chances of being habitable. And if size is misleading, what else about these worlds might be fooling us? To answer that, we have to move beyond averages and densities and look deep into how planetary interiors actually behave under extreme pressure, carbon planets, and diamond worlds, when chemistry flips the script. If two planets can share the same size but hide totally different interiors, what happens when we flip the chemistry of an entire world? In the hunt for alien life, that question matters more than it first appears. Most of the rocky planets we know, including Earth, are built on a simple rule of cosmic bookkeeping. Around most stars, there is more oxygen than carbon in the protoplanetary disk. This means oxygen happily locks up with silicon and metals to make silicate rock and iron cores, rather than leaving much spare carbon to build pure carbon worlds. Our familiar Earth-like recipe is not an accident. It is written into the elemental balance of the system. But while silicate planets dominate our catalog, theory tells us they are not the only option. Imagine a disk where carbon slightly wins the numbers game over oxygen. Water and many oxides would be suppressed. Instead, you would form carbides, graphite, and exotic carbon-rich minerals. So, let's begin to picture a truly carbon planet, black, chemically strange, and forged in a very different kind of furnace. Deep inside such a planet, pressures would crush carbon into something spectacular. Graphite at the surface could give way to thick layers of diamond at depth, potentially stretching for thousands of kilometers. Above that, instead of granite continents, you might walk on silicon carbide rock and tar-like hydrocarbons. Volcanoes would not just spew lava, they could belch carbon monoxide, methane, and other gases in proportions totally unlike Earth's. It should be noted that this would reshape the atmosphere, climate, and even the way such a world reflects starlight. We actually have a famous candidate for this idea, 55 Cancri E. It orbits a sun-like star so closely that a year lasts less than a day, and early data suggested its interior might be rich in carbon, sparking headlines about a diamond planet. However, as more observations came in, especially of its atmosphere and heat distribution, the simple diamond world picture started to crack. The current data are ambiguous. They still allow for a carbon-rich composition, but they also fit models with silicates, magma oceans, and volatile layers. So it's time to find out the truth. We need far better measurements to know what really lies beneath. Even so, the thought experiment is powerful. A carbon planet would likely be darker, absorbing more starlight. Its atmosphere might be thick with hydrocarbons rather than water vapor, with greenhouse effects that do not mirror our own. Could such a world ever be habitable in any familiar sense, or would it host completely alien chemistry for life? Optimistically speaking, if simple shifts in chemistry can build diamond-rich planets, what other bizarre materials might dominate worlds we have not even detected yet? And if entire planets can be made of exotic stuff, what does that mean for the next, even stranger classes of worlds waiting in the cosmic catalog? Rogue planets, worlds without suns. If entire planets can be made of diamond, what about planets that have something even stranger missing, like a star? Most of the time, we define a planet by what it orbits. But what happens when a world orbits nothing at all? These are rogue planets, planetary mass objects drifting through interstellar space, with no parent star to warm them and no sunrise to mark their days. They probably formed inside normal planetary systems, just like Earth, and then were thrown out during violent early reshuffling. This means that not every planet in the universe belongs to a neat, well-behaved family. In any young system, gravity is messy. Giant planets migrate, smaller worlds cross paths, and orbits tug on each other like a cosmic pinball machine. But while most planets eventually settle into stable paths, some are in the wrong place at the wrong time. A close gravitational encounter with a massive Jupiter-like planet can act as a slingshot, pumping up a planet's speed until it escapes the system entirely. It should be noted that stars themselves can join the chaos. When two stars pass near each other in a crowded stellar nursery, their gravity can reach in and disrupt planetary orbits. A once stable, Earth-like world can be nudged just enough that repeated encounters with a giant planet push it over the edge. One last close pass, one last kick of energy, and the planet is exiled into the dark. So what is life like for a world without a sun? At first glance, it seems hopeless. No star means no Goldilocks zone, no visible light, and surface temperatures plunging toward absolute zero. But while the surface would freeze into a global shell of ice, the interior of the planet does not instantly die. It still holds leftover heat from its formation, and radioactive elements in the core continue to release energy for billions of years. Under a thick insulating ice crust, that internal heat could keep subsurface surface oceans liquid, just as we suspect on icy moons like Europa and Enceladus. In the hunt for alien life, we usually look for planets in the right orbit around a star. Rogue worlds suggest a different possibility: habitable oases entirely powered from within, with black skies above and deep, hidden seas below. So how do we detect a planet that emits almost no light and orbits nothing? Here, gravity does the talking. When a rogue planet passes in front of a distant background star, its gravity briefly magnifies that star's light in an event called microlensing. The brightening can last hours or days, and then it is gone, leaving only a curve of data hinting that a dark, unseen world just drifted by. So, let's begin to grasp the scale. Microlensing surveys suggest there could be as many rogue planets as there are stars in the galaxy, or more. Optimistically speaking, that means trillions of starless worlds, each a sealed experiment in isolation. So it's time to find out the truth. If some of those frozen, lightless planets really do hide oceans, what happens when we meet the next class of worlds that bend our idea of habitable even further? White dwarf, red dwarf, and binary systems. Planets in strange neighborhoods. So what happens when a planet does have a star, but the star itself is strange? Because in the hunt for alien life, our sun is actually the exception, not the rule. It should be noted that most stars in the Milky Way are not sun-like yellow dwarfs. The vast majority are small, cool red dwarfs, glowing dimly for trillions of years. Many others live in binary or even triple systems, and some have already died, leaving behind white dwarf embers. This means the same type of planet can behave completely differently depending on its stellar neighborhood. Red dwarf stars are the cosmic workhorses. They sip their fuel so slowly that they outlive the current age of the universe. But while they are stable in the long term, their planets pay a price. The Goldilocks zone around a red dwarf is squeezed right up against the star, so any habitable world must orbit extremely close in. Orbits can be just a few days long. At those distances, tidal forces tend to lock a planet, so one side always faces the star. Imagine an Earth-like world, with one hemisphere in permanent daylight and the other in eternal night. The day side may be roasted, the night side frozen, and only a thin ring of twilight might be truly habitable. On top of that, many red dwarfs unleash powerful flares and radiation bursts. Can an atmosphere survive that? TRAPPIST-1, for example, packs 7 Earth-sized planets into a space smaller than Mercury's orbit, all likely tidally locked, all feeling every mood swing of their red dwarf star. Now shift to something even stranger: planets around white dwarfs. These stars are the exposed cores of dead suns, Earth-sized spheres of carbon and oxygen slowly cooling in the dark. Any original planets close in were destroyed when the star swelled into a red giant, so surviving worlds either orbit far away or form and migrate inward later. The habitable zone around a white dwarf sits incredibly close, only a few times the Earth moon distance. So a habitable planet there would whip around its star in hours to days, lit by a tiny, brilliant point in the sky. As the white dwarf cools, the Goldilocks zone gradually moves inward, but cooling is so slow that, optimistically speaking, there could be billions of years of relatively stable conditions. Binary systems take the weirdness further. Some planets orbit just one member of a pair, but others are circumbinary, looping around both stars at once. From the surface, you might see 2 suns rising and setting, sometimes together, sometimes alone. Seasons and illumination patterns could be wildly complex, yet orbital stability is possible if the planet stays far enough out. So, let's begin to connect the dots. Planet type is only half the story. A rocky, Earth-like world around a quiet sun-like star is one thing. Put that same planet around a flaring red dwarf, a fading white dwarf, or a dancing binary pair, and you get completely different climates, atmospheres, and chances for life. So it's time to find out the truth. If stars can twist habitability this much, what happens when the planets themselves start breaking all the rules of composition and structure, atmospheres, temperatures, and the habitability spectrum? So, if stars can twist habitability, what happens when the planets themselves start reshaping the rules of atmospheres and temperature? In the hunt for alien life, this is where things get seriously interesting. A planet's type is its starting hand. Mass and composition decide whether it can hold on to an atmosphere at all. A small, airless rock with weak gravity leaks gas to space like a punctured balloon, while a massive super-Earth, or mini-Neptune, can trap thick envelopes of hydrogen, water vapor, or carbon dioxide. This means the same starlight can produce a frozen wasteland, a mild ocean world, or a runaway hothouse, depending purely on what the planet is made of and how heavy it is. We usually begin with the classic idea, the Goldilocks zone. That ring around a star where, on a rocky surface, liquid water could exist. But while that picture works beautifully for an Earth-like world, it is far too narrow for the real universe. It should be noted that thick atmospheres can keep water liquid closer in, and buried oceans under ice can stay warm far beyond the traditional habitable zone. So, let's begin to think in terms of a spectrum, not a single ring. At one extreme, we have airless rocks, like Mercury, or many of the inner TRAPPIST-1 planets. No substantial atmosphere, brutal temperature swings, almost no chance for stable surface water. Move up the ladder, and we hit Venus-like hothouse worlds, with dense CO2 blankets and reflective clouds, where surface temperatures soar high enough to melt lead. Then, there are temperate Earth analogs, with balanced greenhouse gases, oceans, and clouds that moderate climate over billions of years. Beyond that sit deep ocean planets, where water might be hundreds of kilometers thick, and icy shells with internal oceans warmed by tidal flexing or radioactive heat. Europa and Enceladus in our own system are the prototypes. They may orbit far outside the Sun's classical habitable zone, yet their subsurface seas could be friendlier to life than some scorched habitable planets hugging a red dwarf. Greenhouse gases, clouds, and albedo, the fraction of light a planet reflects, quietly rewrite the rules of distance. Add methane, or CO2, and a world can stay habitable farther from its star. Cover it in bright ice or thick reflective clouds, and you might need to move closer in to avoid global freezing. Optimistically speaking, this gives nature many different ways to land on just right conditions. So which class will show us the first clear biosignature? A near-perfect Earth twin in a familiar Goldilocks zone, a bulky super-Earth with a stable, dense atmosphere, a hidden ocean world, venting organics into space, or something we have not even named yet? So it's time to find out the truth by looking at the full planetary zoo, every type of planet the universe can build, and what each one does to its atmosphere, temperature, and chances for life. TRAPPIST-1, a compact laboratory of rocky planet types. So if the universe can build such a wild variety of worlds, where can we see many of them side by side, under almost identical conditions? We do not have to imagine that laboratory. It already exists, just 40 light-years away. So let's begin with TRAPPIST-1. TRAPPIST-1 is an ultra-cool red dwarf star, only a bit larger than Jupiter in size, but far more massive, and incredibly dim compared to our Sun. Around this tiny ember, 7 Earth-sized planets circle in a configuration so compact that all of them would fit well inside Mercury's orbit. This means the entire system is like a tightly packed model of rocky planet diversity, compressed into a space smaller than the inner solar system. The orbits are so close that TRAPPIST-1b, the innermost planet, whips around the star in just a day and a half. Outward from there, conditions change rapidly. The inner planets are blasted by more starlight, likely too hot for surface oceans. The middle worlds sit in the traditional Goldilocks zone, where liquid water could exist. The outer planets receive far less energy, probably making them colder, icy worlds. In the hunt for alien life, this single chain of 7 worlds may span nearly every major rocky type. Bare rock, steam-shrouded, water-rich, and volatile-rich. Why did TRAPPIST-1 capture astronomers' attention so dramatically? First, all 7 planets transit, passing in front of the star from our point of view. Each transit slightly dims the star, letting us measure planet sizes with high precision. Second, the planets are all similar in size, roughly Earth-like rather than gas giants, so we can compare them fairly. And third, it should be noted that the star is so small that even a thin atmosphere on one of these worlds leaves a measurable fingerprint in the starlight. Suddenly, atmospheric data for multiple rocky planets in the same system is on the table. TRAPPIST-1 also lets us test ideas we have been building throughout this video. These planets are almost certainly tidally locked, with permanent day and night sides, so we can check how that affects climate and habitability. They all bathe in the same red dwarf spectrum, so we can see how different rocky compositions respond to the same harsh, flaring environment. Optimistically speaking, if any red dwarf system can teach us about habitable Earth-like planets, this is it. But here is the tension. Are these 7 worlds mostly airless rocks, stripped by their star? Are they Venus-like ovens under crushing atmospheres, or deep ocean worlds with global seas and high-pressure ice? Or are they something strange stranger that does not fit our current categories at all. What we discover in TRAPPIST-1 will echo across the galaxy, because if these planets cannot hold on to friendly atmospheres, what does that say about the billions of rocky planets around red dwarfs everywhere? So it's time to find out the truth by looking at what our best telescope, James Webb, has already seen there and what it still cannot yet rule out. How we read alien worlds, transits, wobbles, and spectral fingerprints. If we want to know whether TRAPPIST-1e is a desert, an ocean world, or something far stranger, we first have to answer a deceptively simple question. How do we read a planet we cannot see? In the hunt for alien life, everything starts with turning tiny changes in starlight into a story about an alien world. So, let's begin with the workhorse, the transit method. When a planet passes in front of its star, it blocks a fraction of the light. A small, regular dip in brightness traces out the planet's orbit, giving us the length of its year. The depth of that dip tells us the planet's size. Double the radius, and the blocked area grows by a factor of 4, so even Earth-like planets around a red dwarf can leave a measurable scar in the light curve. This is exactly how the 7 planets of the TRAPPIST-1 system were first revealed, as rhythmic flickers, like a cosmic barcode. But while transits tell us how big a planet is, they do not tell us how heavy it is. For that, we watch the star wobble. The radial velocity method measures the star's motion toward and away from us as the planet's gravity tugs on it. That motion imprints a tiny, repeating shift in the star's spectrum. From the amplitude of that wobble, we infer the planet's minimum mass. Combine that with the radius from transits, and suddenly we have density. Is this world iron-rich and compact, puffed up and gas-dominated, or something in between? This means we can already sort many planets into broad classes: rocky super-Earth, mini-Neptune, or full-blown gas giant. However, density alone can trick us. 2 planets can share the same bulk density, yet hide very different interiors. So it's time to find out the truth by looking at their atmospheres. During a transit, a thin ring of starlight filters through the planet's atmosphere before reaching us. Transmission spectroscopy spreads that light into a rainbow and hunts for missing colors. Specific molecules, water vapor, methane, carbon dioxide, hydrogen, each remove light at characteristic wavelengths. It should be noted that these spectral fingerprints are how JWST can say that a mini-Neptune is wrapped in a hydrogen-rich shroud, or that a hot Jupiter's sky is loaded with water and carbon monoxide. Now we put everything together: radius from transits, mass from stellar wobbles, molecules from spectral fingerprints. From these, we reconstruct bulk composition, mostly rock and iron, rock plus deep oceans, or a small core under a vast envelope of gas. Optimistically speaking, this is how we decide whether a planet sits in a potentially habitable category, or in a class of worlds utterly hostile to life. Yet our taxonomy is still incomplete. Every time a new technique sharpens our view, we find planets that do not fit the boxes we drew. Super puffs lighter than cotton candy, ultra-dense mega-Earths, or airless lava worlds, where we expected gentle oceans. And as we refine these methods on systems like TRAPPIST-1, we are starting to see something even more unsettling: entire classes of planets that may be common in the universe, but completely absent from our own solar system. The question is, where does each TRAPPIST-1 world actually land in this growing planetary zoo? The Cosmic Planet Zoo, building a unified classification. So how do we bring order to this chaos? If the universe is running a cosmic planet zoo, we need a map, not just a list of strange creatures. So let's begin with 3 simple axes that we can keep in our heads. First, size. From sub-Earths, smaller than our world, all the way up through super-Earths and mini-Neptunes, to full Jupiters and even super-Jupiters. Second, composition. Is the planet mostly rock and metal, mostly water and ices, or wrapped in a deep envelope of gas? Third, temperature. Ultra hot, temperate, or cold, set mainly by how close it orbits its star. This means every world we have mentioned can be plotted as a point in this 3-dimensional space. Terrestrial planets like Earth, Venus, and TRAPPIST-1e are small, rocky, and live in the hot to temperate range depending on their distance from the star. Super-Earths push up the size axis, but stay rocky. Mini-Neptunes occupy the next band, larger, lower density, with thick atmospheres that blur the line between solid surface and sky. Then we move to gas giants like Jupiter and hot Jupiters, and finally to ice giants like Neptune, which are smaller than Jupiters but richer in heavier elements and ices. But while that sounds neat on paper, the real universe loves to color outside the lines. Lava worlds are simply ultra-hot rocky planets on this map, hugging their stars so tightly that their surfaces melt. Ocean worlds slide toward the water-rich corner, often in the temperate zone, where global seas or high-pressure ice layers may form. Superpuffs climb high on the size axis, but drop dramatically in density, becoming warm, bloated giants with atmospheres so extended they are almost clouds in search of a core. Pattern interrupt. What about planets with no temperature from a star at all? Rogue planets step completely off the usual grid, drifting through interstellar space with no orbit around any star. They still fit our size and composition axes, but their temperature axis is set by internal heat alone, making them cold, dark outliers in the zoo. It should be noted that this framework is a living one. In the hunt for alien life, telescopes like JWST are already revealing atmospheres that do not fit our expectations. Rocky planets with surprisingly puffy hydrogen envelopes, or Neptune-sized worlds stripped almost bare. Optimistically speaking, future missions may force us to add new boxes for carbon planets, mega-Earths, or hybrids we have not even imagined yet. So it's time to find out the truth about every new exoplanet headline you see. Whenever you hear warm mini-Neptune or Earth-like world in the Goldilocks zone, you can mentally place its coordinates on this map. Size, composition, temperature. Suddenly, the cosmic zoo is not random anymore. It is a structured landscape, and we are just starting to chart it. Where could life thrive? Ranking planet types by potential. Now that the cosmic zoo is mapped out, the real question hits. Out of all these worlds, where could life actually thrive? In the hunt for alien life, which cages in this zoo should we press our faces against first? So let's begin with the obvious favorites. Earth analogs. Temperate, rocky planets with solid surfaces, liquid water, and moderate atmospheres, sitting in the Goldilocks zone of a quiet, stable star. We know this recipe works because we are the proof. A balanced greenhouse effect, a protective ozone layer, and long-term climate stability let complex ecosystems emerge. This means that when we see an Earth-sized planet with a similar orbit around a sun-like star, it jumps straight to the top of the check for biosignatures list. But while Earth twins are emotionally satisfying targets, the universe might be biased towards something else, super-Earths. These are rocky or rock plus water planets 1 to 2 times Earth's radius, probably far more common than true Earth copies, and easier to detect in our data. Their stronger gravity can hold on to thicker atmospheres, smoothing out temperature extremes and potentially stabilizing climate over billions of years. It should be noted that this same gravity also makes tall mountains, large oceans, and even human-style spaceflight much more challenging. Dense air could mean crushing surface pressures, or global clouds that hide any surface signatures from our telescopes. Then, we have ocean worlds and icy moon analogs, the stealth contenders. Think of Europa, Enceladus, or a scaled-up water planet, huge reservoirs of liquid locked beneath ice shells or deep global seas. Inside, tidal heating and chemistry at the seafloor could power ecosystems, even without much starlight. Optimistically speaking, these might be the most common habitable environments in the galaxy, but how do we prove it from light years away? Thick ice or high-pressure water layers bury any biology beneath, making classic atmospheric biosignatures incredibly hard to detect. Red dwarf systems, like TRAPPIST-1, sit at a strange crossroads. Red dwarfs are everywhere, and they live for trillions of years, so their rocky planets in tight orbits offer enormous real estate for life. Yet many red dwarf stars flare violently, stripping atmospheres and bathing surfaces in radiation. Tidal locking can freeze one hemisphere and scorch the other, unless a thick atmosphere or ocean efficiently moves heat around. TRAPPIST-1 is unusually calm for a red dwarf, so it gives us a rare laboratory. If life can adapt to this environment, the galaxy might be teeming with habitable red dwarf planets. So it's time to find out the truth. Will the first clear biosignature come from a tidy Earth-like twin, a massive super-Earth with a deep sky, or some strange hybrid planet that forces us to rewrite what habitable even means? In the next section, we will see how our instruments are racing to answer exactly that: future telescopes and the next planet. Types we haven't named yet. To answer that, we now have to look ahead. If JWST could already shake up our idea of a habitable planet, what will the next generation of telescopes do to our entire planetary zoo? So, let's begin with the hardware that will rewrite the catalog. On the ground, extremely large telescopes like the ELT in Chile will use mirror segments tens of meters across, with adaptive optics that can cancel out Earth's blurry atmosphere in real time. In space, concepts like NASA's Habitable Worlds Observatory promise something even more radical: direct images of Earth-like planets around sun-like stars, not just faint dips in starlight. To pull that off, we need to block the star itself. Future coronagraphs will act like tiny, ultra-precise eclipse makers inside the telescope, while starshade concepts imagine a separate spacecraft flying tens of thousands of kilometers away, casting an artificial shadow. It should be noted that this level of engineering is extreme, but while it's difficult, it is exactly what we need if we truly want to see new worlds as worlds, with their own colors, clouds, and weather. This means our sample of planets will finally expand beyond the big, hot, and easy. Higher resolution and sensitivity will let us probe smaller planets, cooler planets, and planets around stranger hosts. We will be able to study temperate super-Earths that transit faint red dwarfs, frozen mini-Neptunes drifting in the outer regions of their systems, and even worlds around white dwarfs, where the Goldilocks zone hugs a tiny, fading stellar ember. What might we find there? In the hunt for alien life, hybrid water, hydrogen worlds are a strong candidate for a brand new class. Imagine a planet with an Earth-mass rocky core, wrapped in a deep global ocean, and then capped by a thick hydrogen atmosphere that keeps everything warm, far from the star. Is that ocean a pressure-cooked hell, or a stable, long-lived habitat? We may also uncover exotic atmospheric chemistries that do not fit our current labels. Planets with photochemical hazes that turn the sky blood red, carbon-rich worlds with methane seas and soot-like clouds, or close-in white dwarf planets where the star's ultraviolet light sculpts atmospheres into something we have never modeled. So it's time to find out the truth about how flexible habitability really is. As we push to lower masses and cooler temperatures, boundaries will blur. We will detect objects that sit awkwardly between planet and brown dwarf, with failed star cores but planet-like weather. We may see captured worlds that look like oversized moons, orbiting giant planets in the habitable zone, where tidal heating and starlight work together. Optimistically speaking, the most important planet type for life might be one we have not even named yet, hiding just below our current detection limits, waiting inside the raw data of these future observatories. In the next section, we will follow those discoveries all the way to their logical conclusion: what happens when we finally spot a world that does not just look habitable, but actually looks alive. Reframing Earth, our home's true place in the cosmic catalog. So after touring the entire cosmic zoo of worlds, we have to ask a slightly uncomfortable question: where does that leave us? Are we a standard entry in the catalog, or a weird edge case the universe rarely bothers to print? So let's begin by filing Earth properly. In the grand taxonomy we have built, our world is a temperate, mid-sized rocky planet wrapped in a substantial atmosphere, sitting in the Goldilocks zone of a relatively quiet G-type star. It orbits at just the right distance for liquid surface water, with enough mass to hold onto air, but not so much that it turned into a mini-Neptune. On paper, that sounds almost boring. On paper. Because when we compare Earth to the exoplanet population, the story shifts. The most common worlds we see are super-Earths and mini-Neptunes, between 1 and 4 times our radius. Our solar system famously has none of those. This means that, statistically, a planet exactly Earth-sized, in a near-circular orbit around a sun-like star, is not the default outcome. Rocky planets are common. Earth's particular combination of size, orbit, and star type seems to sit in a narrower slice of parameter space than we once assumed. Are we rare, or just hard to detect with current data? It should be noted that our system architecture is also a little odd. Many systems parade hot Jupiters skimming just above the stellar surface, or chains of tightly packed mini-Neptunes. We have neither. Our gas giants live far out, with Jupiter and Saturn at moderate distances and nothing huge plowing through the inner system. The leading idea is that this calm interior may have preserved Earth's long-term habitability instead of shredding or ejecting the building blocks of a temperate, Earth-like world. But while that sounds reassuring, it also raises the stakes. Change that layout slightly, and maybe there is no blue planet here at all. Then there is our atmosphere, which might be the strangest thing about us. Oxygen at 21%, traces of methane, water vapor, and an almost absurd level of chemical imbalance. In the hunt for alien life, this is exactly the kind of spectral fingerprint we dream of finding. Optimistically speaking, Earth is not just a planet type, it is a biosphere type, where life has rewritten the air itself. So it's time to find out the truth this implies when we finally spot another world that looks this unstable, this disequilibrium driven. Will we be seeing a second Earth or something entirely new? In the next section, we will push that question to its limit and ask what it would actually take to declare, with evidence, that we have found life beyond our home, from dust to diamond worlds, recapping the planetary spectrum. So if a strange disequilibrium atmosphere is our best clue to life, what kind of worlds are out there to wear that signal? To answer that, we have to zoom back out and look at the entire menu of planets the universe can cook up. So let's begin where every world starts, in a thin, cold disk of gas and dust swirling around a newborn star. Close in, inside the snowline, it is too warm for ices to survive, so worlds grow mostly from rock and metal. Farther out, beyond that invisible frost boundary, water and other ices freeze, adding huge amounts of solid material. This means some planetary cores grow fast enough to grab vast envelopes of hydrogen and helium before the disk disappears, while others stay small and rocky forever. From that simple gradient, we already understand why we see compact terrestrial planets like Mercury, Venus, Earth, and Mars hugging their stars. Scale those up a bit, and we get super-Earths, with thicker mantles and higher gravity. Scale them down, and we get sub-Earths, airless or barely holding on to an atmosphere. Push a rocky planet too close to its star, and it becomes a lava world, with magma oceans and rock vapor in the air. Move it slightly out and load it with water, and we arrive at ocean and water worlds, where high-pressure ice may lurk beneath global seas. Farther from the star, at and beyond the snowline, the giants appear. Gas giants like Jupiter and hot Jupiters in tight orbit are dominated by hydrogen and helium. Ice giants and warm Neptunes mix rock, metal, and volatile ices. Shrink a Neptune, and we get mini-Neptunes, with thick atmospheres over smaller cores. Puff those atmospheres up with heat and low gravity, and we reach super puffs, planets with densities lower than cotton candy. Crank the mass of a rocky planet to extremes, and we get mega-Earths, ultra-dense worlds, with crushing surface gravity. Change the ingredients, and the picture shifts again. In carbon-rich disks, carbon planets, and even potential diamond worlds could form, where carbides and graphite replace familiar silicates, and sometimes dynamics throw a planet completely out of its system, creating a rogue world drifting between the stars, warmed only by leftover heat and maybe a buried ocean. It should be noted that all of these belong on the same map. We classify them along a few key axes. Size, from sub-Earth to super-Jupiter. Composition, from iron rock to water-rich to gas-dominated. Temperature, from lava-hot to cryogenic. And host environment, from calm sun-like stars to active red dwarfs, and even no star at all. Every exotic headline you see about a new planet is just a new coordinate in this four-dimensional space. In the hunt for alien life, some regions of that space look far more promising. Temperate terrestrial planets and moderate super-Earths in the Goldilocks zone, with stable stars and the right amount of atmosphere, are our best candidates. Ocean worlds and some mini-Neptunes could hide habitable layers, but they are harder to probe. Lava worlds, super puffs scorched by their stars, and most rogue planets are long shots, though not impossible in principle. Optimistically speaking, the more kinds of planets we discover, the more ways we find to assemble the ingredients for habitability. Earth stops looking like a miracle and starts looking like one very specific solution out of many, a mid-sized rocky planet in a quiet system at just the right distance, with just enough water and just the right atmosphere. This means our home is both precious and scientifically explainable. So as we move into the final stretch, we can ask a sharper question. Now that we know the full planetary spectrum, what would it actually look like in our data the day we confirm that one of these worlds is truly alive? Your new superpower, decoding every exoplanet headline. So what do we actually do with this new superpower? If tomorrow's headline screams, "New Earth-like world discovered," how do we, together, decide what that really means for life and habitability? In the hunt for alien life, Every exoplanet announcement is a little puzzle. We are not just spectators reading the headline. We can read the numbers, the orbits, the star, and quietly ask, where does this planet sit in the cosmic zoo we have just mapped out? So, let's begin to build a mental checklist you can use every single time. First question, rocky or gas-rich? If the planet is up to about 1.5 Earth radii and dense, we file it with the terrestrial worlds, super-Earths, or lava planets. Above that, with a puffy atmosphere, it drifts into mini-Neptune territory. This means a thick envelope of hydrogen and helium, probably no solid surface you could stand on, and very different prospects for life as we know it. Next, hot or cold? Look at the orbit and the star's brightness. Is it pressed up close, like a hot Jupiter with a year shorter than an Earth day, or cruising in a Goldilocks zone where liquid water might exist? It should be noted that the same distance means very different things around a dim red dwarf versus a bright sun-like star. Temperature is not just about distance, it is about the whole system. Then, what kind of star is hosting it? Quiet, like a calm orange star, or a flare machine of a red dwarf? Single star, or a tight binary where gravity is constantly tugging? This instantly tells you something about whether atmospheres can survive, whether the planet is tidally locked, and how stable conditions might be over billions of years. Let's test it. Imagine a temperate super-Earth around a red dwarf. You would say, rocky, a bit larger than Earth, probably tidally locked, orbiting close in, but still in the Goldilocks zone, because the star is cool and faint. Around a typical flaring red dwarf, you might worry about the atmosphere being stripped. Around a quieter one, like TRAPPIST-1, you might say, optimistically speaking, that this world could be habitable if it kept its air and water. Now compare that with a hot mini-Neptune around a sun-like star. Instantly, thick atmosphere, likely no solid surface, short, scorching orbit, probably more like a scaled-down gas giant than an Earth-like planet. So it's time to find out the truth about how you see these worlds. In the comments, choose your favorite planet type from this video and explain why, or invent a new class you would love telescopes to find, and give it a name. Together, we become co-investigators, not just watching the universe unfold, but helping to decode it. And once we have this shared toolkit, we can tackle the final question. What would it really take, in our data, to say not just interesting planet, but this world is alive? The next planet we discover might change everything. So what happens when that moment finally comes? When a cold line in a telescope's data quietly crosses the boundary from interesting planet to this world might be alive? It should be noted that only a few decades ago, that question would have sounded almost absurd. We knew 9 local planets, all huddled around one ordinary star, and that was the entire catalog. No hot Jupiters skimming their suns, no super-Earths, no rogue worlds drifting between stars. Just our neat little solar system, and the assumption that it was normal. This means we have lived through a revolution. In one human lifetime, we have gone from 0 confirmed exoplanets to thousands of alien worlds, spread across dozens of wildly different types, super puffs lighter than cotton candy, ocean planets with global seas, scorched lava worlds locked to their red dwarf hosts. The universe has been quietly telling us, you underestimated what a planet can be. In the hunt for alien life, this diversity is not a distraction, it is the point. Somewhere in that growing catalog, there is almost certainly a world with clouds, storms, and seasons as intricate as Earth's. A planet where the atmosphere is not just gas, but chemistry in motion, maybe even biology in motion. Its signal is already mixed into the noise, we just have to learn how to notice it. So let's begin to think of the night sky differently. When you step outside and look up, you are not just seeing stars. Around almost every point of light, planets are circling in silent orbit. Some are baked wastelands, some are frozen deserts, but some sit in that delicate Goldilocks zone, where liquid water can flow and complex atmospheres can breathe. Optimistically speaking, a few of those worlds might one day be more than dots in a graph. They could become targets for future probes, laser sail flybys, or, on timescales longer than our own lives, destinations for very distant descendants. Our map of the galaxy is slowly filling in with real places, not just coordinates. And here's the core of it. Understanding every type of planet does not just answer what is out there, it sharpens a deeper question. Who might be out there to ask it with us? If Earth-like worlds are common, if habitable atmospheres can survive the tantrums of a red dwarf or the slow cooling of a white dwarf, then maybe curiosity itself is not unique to this one blue sphere. So it is time to find out the truth. Subscribe, stay with us, and we will dive into each of these planet types and follow every new telescope result until the first truly Earth-like world, or something even stranger, steps out of the noise. Because the next planet we discover might not just change astronomy, it might change who we think we share the universe with.